Good afternoon, class. Today we're talking about antimicrobial drugs. And so the first antimicrobial drugs discovered were antibiotics, which are naturally produced by microorganisms. For example, the first antibiotic was penicillin, and it is made by the Penicillium fungus, which is the one you find on your orange. And what happened was the man, Alexander Fleming, was doing an experiment with the bacteria, and he got real tired. It was late at night, and he left out his experiment, and when he woke up in the morning, he was upset to find that it had been invaded by mold, and while he was about to throw it away, he realized that there was what we will call now a zone of inhibition around where the bacteria had been killed. And so that was the beginning of penicillin. So penicillin is still one of the best antimicrobial drugs today, and its derivative. Why? Because it has good selective toxicity. So selective toxicity says it can kill the microbe without damaging the host too much. So the host would be the person, the patient. So what happens is it will target the cell wall of the bacteria. So just a quick review, the cell wall, we have peptidoglycan. If it has a thick layer of peptidoglycan, that's called a gram-positive bacteria. And then if it has a very thin layer of peptidoglycan and mostly LPS lipopolysaccharide, that is a gram-negative bacteria. Remember, the gram-negative will stain pink, the gram-positive will stain purple. And so that's called selective toxicity. So the only problem with penicillin was rapidly microorganisms became resistant to it. So we'll talk about that later. But because they're resistant, nowadays before we give a patient an antibiotic, we will have to run a test to see if the antibiotic will work against the bacteria or the infection that they have. So one of the tests we use is called the Kirby-Bauer test. In that case, we take a plate and we plate some bacteria, so the orange are the bacteria, and then we put on these little discs. So the little red things are the discs. These discs have a certain concentration of antimicrobial in them, and we put them in there, and then we will measure what's called the zone of inhibition, which is the halo around where the bacteria have been killed. If it has a small zone of inhibition, it's not going to work as well as these ones that look like eyes that have a large zone of inhibition. So we can do that. The other thing we do a lot is called a dilution test. We take several test tubes, so this is kind of the opposite of Kirby-Bauer, and we put in a certain amount of antimicrobial in there. And then we add an exact amount of bacteria or whatever the pathogen is and see what the effect is. And so this is an increasing amount of dilution, and we can see from that if it is going to be sensitive to the antibiotic or the antimicrobial rather, or if it will be intermediate, which means it works but not that well, or resistant, which means it probably won't work. So that's what we have to do nowadays with our antimicrobial drugs. The penicillins were very good because they target the cell wall. So remember, us as eukaryotes don't have a cell wall, well, except for fungi do and plants. But we humans don't have a cell wall, so that's very good. Something that will hurt the cell wall, usually inhibiting the peptidoglycan, is very good because it will hurt the bacteria without hurting us. So some of the more modern antibiotics they do hurt us. So usually we call them a stronger antibiotic, meaning a different antibiotic, but the side effects might be a lot worse. So unfortunately, we see a lot of resistance to penicillin. There's a lot of penicillins now because we have made some, we have improved them. We have some that are man-made. Remember, an antibiotic is naturally produced by microorganisms. And then we have what's called a broad spectrum antibiotic. That means it can kill a lot of different microbes. However, the bad thing is we have good microbes in our bodies called our flora or our natural biota, and that will kill them too and alter our microbiota and can cause a superinfection. So an example of a superinfection would be, for example, a yeast infection or Clostridium difficile colitis, C. diff. So those are from broad spectrum antibiotics, so they're not without risk. Now, narrow spectrum are the opposite. They will only target something very specific. An example is isoniazid, and I'm not sure if I said that right. Isoniazid is the one that will attack TB, tuberculosis. So that's called narrow spectrum. So that is a little bit about antimicrobial drugs.